So the agenda for today will be I will do a small introduction to Blosc2, then how to extend Blosc2 via plugins. I will discuss also how to do automatic compression tuning with btune, and I will finish with some conclusions. So let's start with a gentle introduction to Blosc2. So Blosc2, it's both a C and Python library. It's also a simple format. So the complete specification is less than 300 lines of text. So this is very simple. Also, it supports full 63-bit containers. So that means that you can store essentially any data for any practical capacity. Nowadays, it is also a fully dimensional, supports fully dimensional double partitioning. I am going to explain this with a little bit more of detail. It also supports different codecs and filters, and it supports meta layers for adding info for applications and users. So here you see the typical Blosc2 container. In the top, we see the header where different applications can write their own header there, and then the data section is composed by different chunks. Okay, and the chunks are split again in what we call internally blocks. And these two components are what we call the double partitioning, right? Because it's not only single partitioning by chunks, but also a double one with blocks as well. So why double partitioning or second partition? It's interesting for dimensional data. So if you see on the left, it is how HDF5 or ZAR or others containers works. They only have one level of partitioning. So that means that if you are interested just in a small part of this cube, for example, this chunk, that means that you need to decompress the whole chunk in order to get access to that data. On his hand, Blosc2 introduces a second level of partitioning, and that means that every cube here is subdivided again in a second partition with smaller cubes. And that means that if you're interested in just a small part of this cube, you will only need to decompress the affected blocks or the affected blocks in that partition. And that leads to much more selective and faster queries in general. So here it's a glimpse on the API for Blosc. So here, for example, we are creating an n-dimensional array. It is 4 by 4 here, and with a fill value 9 here. And then we see that we can resize. We can resize the array as well to make it larger, and then it supports also setting operations. So here we have an example of the output. Here are the 9s of the initial array. Then the resize operations filled everything with zeros, the expansion of the array. And then this rectangle of 8 is the result of this assignation statement here, right? So it's very easy to use, and it tries to mimic NumPy API as much as possible. You can have a look at the reference here. Okay. Okay, so Blosc2 is not only meant for be used in a standalone mode. It is also meant to make other formats more efficient. So here I am going to discuss the HDF5 case. HDF5 is a very well spread format, especially on scientific, but also in business applications. And PyTables and NumPy are two of the most spread wrappers for 2HDF5. So here we can see that for storing, like here we are storing a 4-dimensional array, and here we are doing different slices, for example, in dimension 0, dimension 1, dimension 2, and dimension 3 for the 4-dimensional array. Right? Here in the y-axis we have the throughput in megabytes per second. We can see how if we use the regular filter approach with HDF5 in Blosc2, we can get this performance in blue for PyTables and in green for H5Py. However, if we tickle things and we do a more optimized use of Blosc2 layer in both PyTables and H5Py, we can see that we can get much more performance when we are getting, for example, these slices. And this is because we are leveraging the second partition, right? In this case, PyTables in red, it's a bit more performance than H5Py because the optimization in H5Py happened at the Python level, whereas for PyTables integration has been done much more low level at the C level, and this is the reason. But typically, you can expect, as you can see, between 5 and 8 times better speed by using Blosc2 with the second partition and optimizing for the second partition. Okay. Now, regarding file sizes, Blosc2 also comes with a special machinery that can optimize for sparse arrays. So essentially, what's going on is that Blosc implements a very fast and very easy to run run length compression code codec. And that means that, for example, when we are compressing like a big 3D cube from the Gaia mission, I did. You can find these details on the Gaia mission on a recent talk that I did on SciPy in 2023. And but the idea is that when you are compressing that with Blosc2, you get, for example, here we are using Blosc2 codec, and I mean, Blosc2 can use more than half or less than half of the space that it takes Blosc1, for example. So, for example, here is Blosc2 and Blosc2 with H5Py in red as well. And here it's in red, and in violet, it's ZAR and H5Py with Blosc1. And here is the difference between Blosc2 and Blosc1. When we're using Z standard, the differences are still larger, and we can see that Blosc2 in combination with Z standard provides the best compression ratio for this sparse dataset that is holding 8 trillion cells. That it's almost 8 terabytes. So Blosc2 plus Z standard can pack this entire Gaia array in less than 2 gigabytes. So that means a compression ratio of more than 4,000, which is pretty good. So let me finish this gentle introduction to Blosc2 by saying that we have Python Blosc2 has a counterpart which is called C Blosc2, and which is a C library for with a low-level API for other languages to use, and it leverages Blosc2 multidimensional capabilities from other languages like Rust, Julia, R, or whatever. Actually, the NDArray Python class that I have shown some slides ago, it's a very shallow wrapper on top of the C Blosc2 library. So that's interesting in order to make other languages to leverage Blosc2. It's not only for Python. Okay, so this is the introduction to Blosc2. Now the dynamic plugins. So you can extend Blosc2 also via dynamic plugins. Although Blosc2 supports a wide range of codecs and filters right off the box, there is always a need that is not well covered by the standard suite. And this is why Blosc2 allows users to implement their own ones and register them for being used automatically. Here, it's there is a blog where it is explained how you can register your own plugins. Okay. So how does it work? So whenever CBLOS receives a request for using a dynamic codec ID that is not registered, it's locally registered only. It will dynamically load the DLL library. So here is the CBLOS2 library. And then whenever the user requires a codec or filter, which has a different ID that is inside of the CBLOS, it tries to use DL open and load library in order to load the codec dynamically, the dynamic library from the operating system. And then it uses the compress and the decompress in order to do all the job. Okay, let's retake. So I think I started with the dynamic plugins like 3 minutes ago. Let's quickly recap what from the pros and cons. Okay, not that bad. Okay, good. So pros and cons, and yeah. So the pros is that it's very easy to install because you can provide wheels for the plugins, and there is support for C, C++, and Rust as well. The cons is that, I mean, creating a plugin for Blosc2, it's a little bit more work to create, but we are providing an example with detailed instructions here. Okay, so you can follow. It's a full example where you can follow all the steps for doing that, and also for creating wheels for that. As a practical example, let me introduce Blosc2 Grok, which is a plugin for JPEG 2000. So it's a lossy compressor. So typically Blosc2 normally only includes lossless compressors. So this is a good contribution for Blosc2. As you know, JPEG 2000 is a high quality lossy compression for images. For doing this plugin, we have chosen Grok, which is an open source JPEG 2000 implementation by Aaron Boxer, and you can install it very easily with the binary wheel. Here is an example of use from Python. Let me show you how it works. So here on the left we have the original image without with lossless compression, and then here it's JPEG 2000 via Grok, and you can see that even if the size is 3 times less, I mean we are losing very little details. So this I mean this codec is really nice for compressing images in Blosc2. Even if we choose a more extreme lossy compression parameters, we can see that, for example, in this case, we are reducing a factor of 10 with on the right side in respect to the lossless image, and we can see that we see very apparent artifacts, but the image is still okayish, right? So yeah, that's a pretty good implementation, and it's a very nice example of how you can extend Blosc2 with your own codecs. Okay, so this is for codecs. Now let's explain a little bit about btune. So btune, it's about making compression better. btune is exactly it's a state machine where the package has different states, and in every state it is evaluated the different compression parameters like the codec filter and shuffle and size, number of threads, different parameters. So, for example, here you can see an example of that, how that works. So at the beginning, in the initial state, different codecs are tested in combination with different filters, okay? And then some scores are evaluated, and BTune keeps track of the best results so far, right? And it is the best results are marked, and they are suggested to be used in the end, okay? So this is how it works, and you can see the flow between the different states in the machine state. So this is how it works. But also, it can also be trained to find the best codec and filter with using deep learning. Actually, there are three mainly operation modes for BTune. The first that I have shown is the BTune genetic, because it's essentially a genetic algorithm that tests different combinations of parameters to select the best combinations. Then there is BTune models. It uses deep learning. In this mode, you send, or the Blosc development team helps you finding a neural network model adapted to your data sets for faster operation. And then there is BTune Studio, where you can use the training package locally to generate your own models for your data sets by yourself. Installing BTune is very easy. It works like a plugin, so you can install typically with pip. And using it is easy. You typically provide a hint to BTune where you specify the trade-off that you want for your compression. So, for example, if this trade-off value is near 0, that means that you prefer more speed than compression ratio. Whereas if the trade-off is towards 1, that means that compression ratio is more important than the speed, right? And then you activate also the tracing, so you can see how the machine state is evolving towards time. There are several tutorials that I already done. The first one is I did that a couple of hours ago in this conference, and you can have a look at the tutorial also online if you are interested in trying that. Okay. BTune models, as I said, typically BTune can be trained also for data sets. So that means that BTune can infer in real time the right combination of codec and filter that suits the requirements for different chunks, okay, that you are compressing. So you can favor speed, favor compression ratio, or trade-off, everything automatically after the training has been done. So essentially what is done is the training process generates a model, a neural network model. And here we have an example of the predictions for the Gaia dataset, where we see that depending on the trade-off, different combinations are chosen. Here are estimations of the compression ratio, compression speed, and decompression speed in gigabytes per second. And here we see an example of the speed. Of course, when the trade-off is more towards speed, we can get it's in blue. We can get better speed. But when the trade-off is more towards compression ratio, speed is reduced. Although if you throw enough number of threads, I mean, this reduction in speed is not that important. So it depends on your machine if you want to choose one trade-off or another. And of course, the predictions are much better when the codecs that has had to be chosen differs more in features. So, for example, in this case, in red, this Blosc LZ, and in blue and in green is LZ4, and both have very similar features. So the predictions are quite random, so to say. However, if we choose between Z standard and blocks LZ, which expose very different features, the predictions are very, very accurate, which is the most important case we want to distinguish between these scenarios. Here are some testimonials about people using BTune. They are very pleased in general to use that because it provides like a nice feedback for choosing the different compression parameters. So in conclusion, Blosc2 is providing a novel way to handle huge and dimensional arrays representing large volumes, tested up to 8 trillion cells, and much and more can be done probably. It can be extended via dynamic plugins, and BTune allows for automatic selection of the best compression parameters. All in all, Blosc2 represents a highly efficient and flexible tool for compressing your data your way. So I always like to thank donors and contracts, because without them it couldn't be possible to produce Blosc anymore. And more on a personal note, I would like to thank NumFOCUS. I've been the receiver of the Project Sustainability Award in 2023. So that will encourage me to put more enthusiasm in the project. So thank you on behalf of all the Blosc team. And in case you have some questions, I will be glad to take them. Thank you.